What if I told you that you could draw the universe? I mean, really sketch out the fundamental dance that builds reality itself. What would that even look like? Well, it might look something like this. And believe it or not, this little drawing right here, it holds the secrets of the cosmos.
Now, I know what you're thinking. It looks like a doodle, right? But this is not a doodle. It's a map, it's a story. Heck, it's a whole language that tells us exactly how the subatomic world works. And today, we're gonna learn how to read it, we're gonna find out where it came from, and most excitingly, where it might be taking us next.
So what is it officially? This is a Feynman diagram, named after the brilliant physicist Richard Feynman, who came up with it back in 1948. And you have to understand, before this, the math you needed to describe even simple particle interactions was just a nightmare. I mean, monstrously complicated. These diagrams, they completely revolutionized physics. They took all those insane formulas and turned them into a simple, visual playbook for the quantum world.
All right, so a quantum playbook. How does it actually work? Let's dive in and break down how this simple little sketch organizes the whole complex dance of particles.
Okay, to really get why this was such a game changer, you gotta know what came before. Physicists used something called perturbation theory. And trust me, it was a nightmare of bookkeeping. For every single event, you had to track just countless mathematical terms. It was messy. Feynman's genius was to create a system where just one of his diagrams could represent a whole bunch of those clunky, messy terms all at once. It wasn't just a simplification, it was a revolution.
So, how do you read one? It's actually pretty simple. Think of it like a comic strip for particles. See those lines coming in? That's your before, the particles in the past. Then, bam! They meet at a vertex. That's the main event, the interaction. The line connecting them in the middle, that's the force being exchanged. It's called a propagator. And the lines heading out, well, that's the after, the particles in the future. Past, present, future. A whole story, all in one elegant little picture. Now, you know, something this brilliant doesn't just pop into existence out of thin air. It stands on the shoulders of giants. It's built on these incredibly profound ideas that came before it. So let's zoom out a bit and trace its intellectual DNA. Okay, check out this timeline. The path really starts way back in 1864 with James Clerk Maxwell. He's the guy who gave us the modern idea of a field. You know, the concept that forces aren't some kind of spooky action at a distance, but are actually carried by something that fills all of space. A huge step. But then in 1918, a mathematician named Noether came along and delivered the absolute master key. And this is the heart of her discovery. I'm not exaggerating when I say Noether's theorem is one of the most beautiful and powerful ideas in all of science. It's so profound. Basically, it says that for every symmetry you find in nature, you know, something you can change without changing the outcome of an experiment, there's a corresponding thing that must be conserved. It was a total paradigm shift. It moved physics away from just thinking about forces and towards the much deeper, more fundamental idea of symmetry. Okay, so what does that really mean in practice? This table makes it super clear. Think about it. If the laws of physics are the same now as they were a second ago, that's a symmetry in time, right? Well, because of that, energy has to be conserved. If the laws are the same here as they are across the room, a symmetry in space, then momentum is conserved. And if it doesn't matter which way you're facing when you do an experiment, that's rotational symmetry, then angular momentum is conserved. This is the amazing part. These conservation laws we learn in school, they aren't just random rules. They are a direct result of the fundamental symmetries of our universe. How cool is that? All right, so where is all this going? We have fields, we have these deep symmetries, and we have Feynman's awesome diagrams. Well, all of these ideas come together in what is, without a doubt, the single most successful scientific theory humanity has ever created, the Standard Model of particle physics. Now, I know this line of text looks super intimidating, all those letters and numbers, but don't worry about the name. The concept behind it is actually pretty straightforward. The Standard Model is built entirely on Noether's big idea about symmetry. Physicists started by defining a set of core mathematical symmetries, that SU3 times SU2 times U1 is just their technical name. And get this, from those symmetries alone, the existence of all the fundamental particles and forces we know about just emerges. It becomes a mathematical necessity. Everything, that is, except gravity. So how well does this model actually work? The answer is ridiculously well. I mean, it's so accurate it's hard to even wrap your head around.
Predictions made using the standard model, calculated with our friend the Feynman diagram, match experiments with just astonishing precision. For example, the theory predicts a property of the electron correctly to 1 part in 100 billion. 100 billion! To put that in perspective, that's like measuring the distance from New York to LA and getting it right to within the width of a single human hair. It's just incredible.
But, and you knew there was a but coming, right? Here's the big twist. For all of its jaw-dropping, mind-boggling success, the standard model isn't the final word. Our quantum playbook, as perfect as it seems, has missing pages.
So, we have to ask the question, what's missing? What's not in this picture? What huge cosmic truths are hiding just beyond the edge of our diagrams?
Yeah, it turns out a lot, a whole lot. The standard model has absolutely nothing to say about gravity. Zero. It can't explain dark matter, that invisible scaffolding holding our galaxies together. It has no clue what dark energy is, the mysterious force blowing the universe apart at the seams. It doesn't explain why neutrinos have mass, or the huge mystery of why there's so much more matter than antimatter. Get this, our nearly perfect theory only describes about 5% of the stuff in the known universe. Just 5%.
And this is where we get to the absolute bleeding edge. This is the frontier. To solve these massive mysteries, physicists are pushing into territories so bizarre, so strange, that the very foundations of reality, I'm talking space, time, information itself, are all being called into question.
So just to give you a little taste of these frontier ideas, let's look at one really speculative framework. It takes a concept we all kind of know, entropy, and flips it on its head. Now, we usually think of entropy as just randomness or disorder, right? But what if it's not? What if it's actually a measure of unresolved recursion? You can almost think of it like a question the universe hasn't finished answering for itself yet, an informational potential. Now, why does that matter? Because a perspective like this totally reframes something as fundamental as gravity. You know, in Einstein's picture, mass tells spacetime how to curve, and that curvature is gravity. Simple enough. But in a model like this one, mass doesn't curve spacetime directly. Instead, it's like it creates a bottleneck in some deeper underlying information system. And what we feel as gravity is actually the pressure, the compression inertia from that informational bottleneck. And that leaves us with one last, really big, provocative question. We started this journey with a Feynman diagram, a beautiful, elegant language for telling the stories of particles. But what if those particles and their stories aren't the fundamental reality? What if they're just the surface level? Is it possible that the universe isn't really a story told with particles, but is instead a vast system of information that's busy telling itself? A system where the particles, the forces, and even the diagrams we draw are just the grammar it uses to write its own story. I'll leave you with that.